Hello there, welcome you back. In the outset of this video, let me presage to all of you about my new lecture series, which is most intriguing and prevalent in the world with the very most important name, relativity, and which is just simply two kind of branches. First is prevalent, pervade in the world with the name the general theory of relativity, and another is the special theory of relativity. First of all, we will understand to know about the general concept of relativity, and which is just a simple word, and I hope you have heard about this word relativity in your intermediate classes or in your primary education also. So what is exactly meaning by the relativity? We will take a look of them, and after that we will study the higher concept on the relativity related to the graduation and the post graduation also. Okay, so first of all, before begin this topic, let us consider what are the key points, the key factors to know what are the key factors which help us to know the relativity subject of the physics. Okay, so the most important word related to the relativity is frame of reference. I hope all you have been heard this word in your 9th class and very well in 11th class. Okay, so what is the exactly meaning by frame of reference, and why we need why we have need to a frame of reference, and what is the frame of reference, that the coordinate of a system in this frame of reference. So what is the exactly meaning by the frame of reference? Let us take a look first on that. Okay, so our topic is frame of reference. I hope all you know about the one fact of the physics, that what you are studying and what you had been studying up till now in the physics or in the science, that is all about the comparison. What we study in the world related to the science, then everything after you are studying, you will look at that everything is a comparison. For example, in physics, when you measure some quantity of anything, like if you are weighing something, let the weight of this thing is 2 Newton, or the mass of this thing is just 2 kilogram, then you are saying the mass of this thing is 2 kg. Okay, so what is exactly meaning by the 2 kg? The 2 kg meaning is that it is 2 times heavier than such kind of body which has 1 kg of mass. Okay, and if you are saying that this length is having the value of 5 meters, then you are comparing the length of this thing with 1 meter of the length of anything. Okay, so comparison always takes place when you study in the physics or in any other branch of the science. Okay, so whenever you know about the study, whenever you come across to the relativity, then you have to remember one thing, that everything is comparison with each other. If you are studying about one thing, then you are surely comparing this thing to another. Okay, I have taken some example, these two kinds of phenomena. Okay, so frame of reference, what is the meant by the frame of reference? Let us consider an event. Okay, so for example, I can take right now an example of a moving train. Okay, so let us consider this is the train which is moving in this direction with a speed 40 km per hour. Okay, now let us suppose that there are the 3 persons. One is A, which is at rest on the ground. Okay, other person B, which is moving along in the direction of the train. Okay, with the speed, let's say it is moving with the speed 10 km per hour. And let us consider another person which is moving in the opposite direction. Let this is C, in the opposite direction of moving train with the speed, let's say same kind of the speed, 10 km/h. Okay. Now these are the three observers which are observing the speed of this train. Okay. Anyone said to you that the speed of this train is 40 km/h. Okay. So what are the observations of three persons according to them? This person will say the train is moving 40 km/h as it is, because it is at rest on the ground, and it is at rest, and so its velocity or speed is 0, and whatever the speed with which this train is moving, that will be observed by this person because it has its velocity as 0. So again you are comparing the velocity of this person to the velocity of the train. This is the comparison. So relativity will take place. Okay. Now if we are interested to ask this person that what is the speed of this train according to you, then what will this person say? This person will say the train is moving with the speed 40 minus 10 equals to 30 km/h, because it is already moving with 10 km/h in the direction of train. So 10 km/h should be subtracted in the speed of this train. So the observation of the velocity of the train according to this person will be 30 km/h, but actually the train is moving with 40 km/h according to the observation of this person. Now what about the observation of this person? Say this person is moving in the opposite direction of the motion of the train with the velocity or speed 10 km/h. Okay. If you are asking about the speed of the train to that person, namely C, he will say or she will say the train is moving with the speed of 40 minus 10, because the velocity of this person, the speed of this person in the negative direction. So the speed of this person will be 50 km/h, because this person is already going in the opposite direction of the train. So it will observe the speed of the train as 50 km/h. What actually I am again saying, the real speed of this train is 40 km/h. Now which one is correct? Now this is a difficulty to say that which one is correct observation of the actual value of the speed of the train. So here this is a difficulty. Now all the three persons are saying truth, because they are saying their respective speed 40 km/h, this is saying 40 km/h, this is saying 30 km/h, this is saying 50 km/h according to their full complete observations. So these are individually corrected. Now which one is correct? So whenever you are asking about the velocity, or you are measuring about the velocity or any other physical quantity, then you are comparing that physical quantity with the another physical quantity of the same kind, with the another value of the same kind of the physical quantity. So this is the comparison. Now in order to get rid of this difficulty, we assume such kind of a system. Okay, this person is standing on the earth, so this is a kind of system. Okay, and this person is moving in the direction of the train, so this kind is another of the system, and this person having the velocity 10 km/h in the opposite direction of the train has some other kind of system. So these all three persons can take three different kind of systems according to which they are saying the velocity of the train according to their observations. So to get rid of this difficulty, we need to assume certain kind of system which is simply known as frame of reference, because they are framing their observation according to their corrected value, their occurring values. Okay, so such kind of a system which can well define the observation of event is known as frame of reference. Okay, so frame of reference is nothing but it is such kind of system in which you can observe the event, you can understand the event, what is actually happening, what are the results of this phenomena or event, like that. Okay, so frame of reference, such kind of system with the context of which you can measure, you can understand the phenomena of the physics or the science. Okay, generally the simplest frame of reference, if you are interested to know about that, is the system, just Cartesian coordinate of system. Okay, Cartesian coordinate system. And what happens in this system? In this system, it is a very simple thing that you can understand any phenomenon or any event by expressing that event, that particular event, in the terms of some coordinates. You are very well known, we are very well aware about the coordinate system. Okay, they are the three axes, x and y and z, which are mutually perpendicular to each other. And if there is a particle, or if there is an event which is happening in the 3D or 2D dimensions, then the coordinate of that particular phenomena can be expressed in x, y and z coordinates. Okay, so if there is a particle which is in the system of 2 dimension, let's say this is the x axis, this is the y axis. Okay, and there is a particle p and particle of phenomena p, okay, or event p, then the position or location of this particle can be well expressed in terms of coordinates x and y. Okay, so I have made a frame of reference in which the location of this particle p can easily be understood by these 2 coordinate x and y. Okay, if this particle is situated in the 3D condition, or it is moving in the 3D plane, or in the 3D kind of motion, then we will require 3 kinds of coordinates x, y and z, because it will somewhere in the x, it will somewhere in the y, and it will somewhere in the z as well. So we will need such kind of system which should be expressed in three coordinates x, y and z. So here we can consider a Cartesian coordinate system. It can be xy 2D system, it can be 3D x, y and z system. Why it is called the Cartesian coordinate? Because x, y and z are simply come in the Cartesian geometry. Okay, so the well defined system of frame of reference is just Cartesian frame of reference. Generally in the Cartesian coordinate system frame of reference, we can observe a particle. Again, let's say this is a particle p, its location is x, y and z, x, y. Then the position vector of particle p with respect to origin O can be expressed as vector r equals xi plus yj plus zk. About this you can very well know only xi plus yj, because this is a 2D system. Okay, what will happen if this would be 3D system? Then in that particular kind of condition, let's say particle p is here, I am drawing it as here, the coordinate in z axis, let's say, is z. Then the position vector of this particle p would have been expressed as zk. Okay, now what will happen if this particle p is moving with certain velocity v? Then its position vector will also be changing with respect to time. Okay, so we can find its velocity and acceleration as well. So if you are interested to find the velocity of this particle p, if it is in motion, then that will be first derivative of this position vector. Okay, rate change of position vector gives you what? The velocity. Okay, so let's say that is v, and v is nothing but the rate change of position vector with respect to time. So that will be d of dt of xi plus yj and plus zk. Okay, now I, j and k are the three unit vectors along x, y and z direction respectively. So these are the constants, unit vectors. Then the differentiation of dx over dt will take place, and also that will be dy over dt times of j cap and plus dz over dt kinds of k cap. Okay, so this is what we have, the velocity. Also you can express this formula in the terms of acceleration also. Differentiate this equation one more time, then that will give you dv over dt, and this will become d square x over dt square, and that will be I times, and plus this will be d square y over dt square, and that will be d square z over dt square. This is what we have, acceleration. So all these formulae, all three formulas are expressed in this Cartesian coordinate system, which is the frame of reference, which is one kind of frame of reference, 3D kind of frame of reference. Okay, so up till now you would have been considered that we need to a frame of reference whenever we want to define, we want to express, we want to demonstrate a phenomena or location of the particle in the physics or in the either kind of science. Okay, also let us discuss the kinds of frame of reference. So generally there are the two kinds of frame of references. One is inertial frame of reference and another is non-inertial. Non-inertial frame of reference. Okay, so first we will look at the first kind of the frame of reference, which is very well known as inertial frame of reference. Okay, so inertial frame of reference is such kind of a system in which all the fundamental laws of science or greatly the physics are valid as they are. So you can just define the inertial frame of reference that it is a kind of a system in which all the fundamental rules like laws of motion and linear conservation of momentum, angular conservation of momentum and energy conservation of momentum can be valid. This is first kind of system. Also you can define it as also that inertial frame of reference is such kind of frame of reference in which Newton's first and second law are true. Okay, so first Newton first and second laws are true. That kind of system, its simple mean is that if you are observing a phenomena and at that place Newton's first and second law is not violated at all, then that phenomena is occurring, that event is happening in inertial frame of reference. In the universe there are a lot of kind of inertial and non-inertial frame of references. How you will distinguish, how you will identify this is inertial and this is non-inertial? You have to look one thing, that if the Newton's first and second law is valid there, then you will able to say this is first kind of frame of reference, and if it is not so, then that will be another kind of, which is known as non-inertial frame of reference. Okay, so this is just a simple phenomenon. What is exactly meaning by this? We will prove that Newton's first and second law are true. After some time they will prove that Newton's first and second laws are true in the inertial frame of references. So before that, let us consider one more important thing about the frame of references. Inertial frame of references is also known as Newtonian frame of reference or Galilean frame of reference. Okay, Gallilean was also a great scientist. So we are discussing about the Newtonian and Galilean frame of references. Okay, so one thing also you should know about the frame of reference, that if we consider Earth, that which kind the Earth is, which one kind of the Earth is as inertial frame of reference or non-inertial frame of reference. So let us consider a phenomena that a particle is at rest. Okay, so this is a one frame of reference in which a particle P is at rest. Okay, now let us consider that this complete system is accelerating with some acceleration A. Now there are the two observers, one is in this frame of reference and there is at outside from this frame of reference. Okay, now if you are interesting to know about the acceleration of this particle P according to this observer and according to this observer as well, then what will be the result, what will be the feedback given by A and B. If you are asking about this, about the acceleration of this particle P with this person A or with this observer A, he will say that P is at rest because it is also in this frame of reference. So both R is at rest, both are at rest. So that rate change of particle P, rate change of position particle P with respect to A is 0. So A will observe P as at rest. So the acceleration of particle P with respect to A will be 0. Okay. Now if you are interested to find the acceleration of particle P according to this person or observer B, he will say particle P is also accelerating with the acceleration, what the acceleration of this system A. Now where the V is in the another frame of reference. Now let us first ensure that where the V is exactly. Let us say that V is at rest in the outside. Okay, and this complete frame of reference, let's say this is S, is accelerating with the acceleration A. Now P will also appear YB accelerating with the acceleration A. Now such kind of system is simply known as inertial frame of reference. Here the feedbacks are, if the acceleration of a particle P is observing by the another observer B in the outer space, then that kind of frame of reference is known as inertial frame of reference, as well as the acceleration of the particle P with respect to such kind of observer which is also in that particular frame of reference should be 0. So it is true, the acceleration of the particle P according to the observer A is 0. So this is simply known as inertial frame of reference. Okay. Now if we are taken the example of the Earth, you know very well Earth is moving around this sun. If this is Earth and it is moving around this sun, as well as it is moving around its own axis. So Earth has two kinds of motion. One is spin motion and there is rotating motion. Okay. Now if you look this Earth from here, let us you are A, then if there is a phenomena, an event which is occurring on the Earth, then that will change its position by two kinds. One is due to this spin kind of motion and the other would be due to its rotation kind of motion. Okay, so in all conditions, all situations, the observations covered by A of an event happening at the Earth will be differ. So this just insimilarity of the earth makes it as a non-inertial frame of reference. Okay, now let us discuss about the important topic, which is simply known as Galilean transformation. So what are the uses of Galilean transformation and relativity? Let us first know about them. So Galilean transformations are nothing but they are gently used to convert the coordinates of a particle or an event from one type of frame of reference to another, and which should be the inertial frame of reference. So I am writing it as, if there is a S frame of reference, okay, and it is inertial frame of reference, and this is another kind of frame of reference, this is S dash, okay, and there is a particle P here whose positions are x, y and z, and in time it is as t, space time at t. And if we are interested to convert its the space time coordinates into this frame of reference, then we will use the Galilean transformations. Okay, so let us sum up the use of Galilean transformation. Galilean transformations are used to convert the coordinate of a particle from one kind of inertial frame of reference to the another kind of frame of reference, which should be also inertial. Okay, so there will be 2 or 3 cases in which we can use of Galilean transformation. Okay, so first of all, we are considering 2 frame of references which are inertial in nature. So let us consider this is one kind of inertial frame. Let's say this is S frame of reference, and this is the x-axis, this is y, and this is z-axis. Okay, and let us consider another frame of reference, inertial frame of reference, which is moving in the x-axis with a constant velocity v. This is another frame of reference. Let's say this is S dash, this is x-axis, this is y-axis, sorry, this is y-axis, this is y-axis here, this is z-axis here, and this is also z dash axis, and this is y dash axis, and this is x dash axis, and this is let's say this is x axis for the first kind of reference of frame. This is x dash axis. Okay, now this complete system is moving with velocity v in the positive x axis direction. Now if we consider a phenomena P or particle P here, whose position coordinates observed in the first kind of inertial frame of reference are x, y, z and t. If you include t in the coordinates x, y, z, then you will say this is the space time coordinate of a particle. Okay, space time coordinate, let me write here, space time coordinate are x, y, z and t. It's mean the Cartesian coordinate plus time at which that phenomenon, that event is occurring. Okay, so the particle P, which is at here, its coordinates, space coordinates are x, y, z and t, which are observed in the first kind of inertial frame of reference. Okay, now this kind of frame of reference is moving with velocity v in the direction of x axis. Then if an observer which is situated at the origin of this frame of reference, let's say O dash, and the origin of this frame of reference is O, then these are the observations observed by in this frame of reference. Then the observations of the location of this particle P observed from this frame of reference will be differ, because it is moving with velocity v with respect to first frame of reference. It is moving, this is situated here, this is at rest, and it is moving in the x-axis with velocity b. So if there is a kind of a person in the frame of reference s dash that will observe differ the coordinate of this particle p according to their on observations. Okay, let's say they are x dash, y dash, z dash and t dash of the same particle p. Okay, now what are the relations among x dash with x, y dash to y, z dash to z and t dash to t? So by using Galilean transformation we can relate x dash to x, y dash to y and z dash to z and as well as t dash to t. Okay, so as I have told you, this particle p is separated as at x distance from first frame of reference. Okay, and also it is separated in the y distance in the y axis according to this frame of reference, and it is also separated, in the z axis, okay, with the coordinate as z. Okay, so let me write down here only x coordinate. Okay, now this particle p or this phenomena is observing in the frame reference s at time t, and after time t this s dash frame is moved up to here. Let us suppose that o dash and o were coincide at a point t before time t, and after time t it will covered as vt distance. So this is distance as vt. After time t s dash frame is moved from o to o dash as distance vt, because distance is nothing but velocity into time, and velocity is v and time is t. Okay, so now you can easily relate that what and this distance from s dash, this is x dash, because particle p is observed by o dash according to s dash frame of reference as x dash, and the y axis y dash and the z axis this is z dash, and in terms of time that is t dash. Okay, so what is the relation between x and x dash and vt? That is x is equal to vt plus x dash, or x dash equals x minus vt. Okay, what about y dash? Particle is here, and when you observe this particle p according to o dash, particle is also at a distance y, because there is no changing in the direction of the y axis as well as in the z axis, because this frame of reference is only moving in the x axis, only in the one directions. Okay, so there will be no change along the y axis and z axis. Okay, so y dash is just y and z dash is just z and t is just t dash, because after time t the time becomes t dash. So these three are the relations, four are the relations which are relating to x dash to x, y dash to y, z dash to z and t dash to t. So this is the first case when another frame of reference is moving with some velocity all in one direction, which is along the x axis, positive x axis. Second case may be if frame of reference s dash is moving in any direction, x, y and z as well, in all three directions. Let's say it is moving in all three axes. This is s dash, this is s, this is y axis, this is z axis, this is x axis, and this is x dash axis, this is y dash axis, this is z dash axis. Okay, now you can easily see that if there is a phenomena or event p here whose coordinates are x, y and z and t observed by an observer which is placing at O in the frame reference S or x, y, z and t, then after t time it has moved somewhere in the x-axis also, in the y-axis also, in the z-axis also. You can easily see that this is a movement in the x-axis, okay, and this is a movement in the y-axis, and this is a movement into z-axis, okay. So let us say that after t time it is separated from here to there. Let's say this is O dash, observer in the S dash frame of reference. So let us say that they were also coincide O and O dash before time t, and after time t S dash has moved up to this position. So, and also it is moving with a certain velocity, the constant velocity with v. So somewhere the velocity will be vx in the x-axis, and if we multiply with the velocity with the time, then that will give you the displacement or distance. Vx times of t is the displacement or the movement in x-axis, and this is vy times of t. This is vy times of t, velocity in y-axis multiplied by time. This will give you the movement of the frame reference S dash into the y-axis, okay, and vz times of t will give you the movement of the S dash with respect to S in the z-axis, okay. Now you can also relate x y z t into the x dash y dash t dash. Let's say x dash y dash z dash t dash, which are the coordinates observed by observer O dash in the frame reference S dash. Then what should be the relation between x dash? This distance is simply x here, and this distance simply is y here, okay, and this distance is nothing but is like this, because this z-axis is here, so its distance in the z-axis is just z, okay. So according to x, this separation is x dash, sorry, this position is x dash here, the position of the p according to this S dash, this is x dash. X is the the position of the p in the x-axis according to S frame, and the relation among x dash, x and bxt is nothing but x dash is equals to x minus vxt. I am repeating, x dash is equals to x minus vx dt. So this is vx x minus vx dt, okay. So vx dt. Also we can easily say that this is the y dash of the particle p position in the y-axis. So this is the complete y, this is y dash. So y equals to vyt plus y dash, or y dash is nothing but y minus byt, complete minus byt. So this is y minus vyt. By the symmetry, you can write the coordinate of z dash in the S dash frame, z minus vzt, and as time is absolute, so there will be no change in the time coordinate, t dash will be like t, okay. So this is just the second case of the Galilean transformation of one kind of coordinate system observed in first kind of frame of reference into the other kind of frame of reference, okay. Now we can formalize a general term or general expression for the Galilean transformation, okay. So let us consider that again. This is the frame of reference S, which is simply the inertial frame of reference. Here O is the observer, this is the x, this is y, this is z axis, and somewhere there is another frame of reference S dash, which is moving with velocity v in 3D space, okay, and this is the observer O dash, and there is a kind of particle here or phenomena p is here, okay. So the position vector of particle P with respect to this frame of reference S will be like this. Let's say this is R. Okay, and the Poisson vector of particle P from O dash will be like this. This is nothing but R dash. Let's say this is R dash, and O and O dash, let's say O and O dash is this. Okay, again let's say this system S dash is moving with velocity b in a 3D space with respect to S. Okay, so after time t, O dash is separated from O by the distance Vt. Okay, I am repeating that the distance covered by S dash with respect to S after time t will be Vt. So O dash was here, and after time t it is at here. So the distance separated from here to there is just Vt. Okay, now this is a triangle OP, O dash. So by the vector sum of triangle O, you can relate R dash and Vt, like here R equals vector R dash plus Vt. Okay, and also R dash equals R minus Vt. So this is a general expression or expression or formula of Galilean transformation of a phenomena P or particle P, which are observed from one kind of frame of reference to the another kind of frame of reference. Okay, here Vt is nothing but the distance separated by the frame of reference S dash, which is moving with velocity v with respect to frame of reference S, which is at rest, and vector R is nothing but the Poisson vector of the particle P or phenomena P or event P with respect to first frame of reference which is at rest, and R dash is the Poisson vector of particle P from such kind of frame of reference into which you are comparing the generalized coordinates or coordinates of the particle P. So this is how the Galilean transformation are worked to relate the coordinates of particle P from observed from one system to another. Okay, now let us discuss one more thing here also, that is the Galilean transformation invariance. Invariance in velocity and acceleration. What is the meant by the word invariance? Invariance is used in such places where there is no change, where there is no change in a physical quantity, which is it is now as it was. Okay, so invariance say is such kind of a phenomena in which there is no change in a physical quantity or in any kind of thing. Okay, so what is the invariance in velocity and acceleration according to Galilean transformation? Okay, so let us denote velocity of a particle in 3D space. This is Vx, V equals to Vxi and Vxy j and Vzk. This is the velocity vector of particle P which is moving with velocity b, or this is the velocity of frame of reference just in the first kind of expression. So this is the velocity b of frame of reference S dash with respect to S in the 3D space. Now if we are interested to find the velocity change, again this is a frame of reference S, this is the frame of reference S dash, there is observer O dash, there is the observer O, Now the velocity, let's say there is a particle p here, okay, and it is moving with certain velocity b, and the velocity b is observed by this observer O. Now O dash will observe the same kind of velocity of particle p having a different value. So what are the relation between the v dash and b? V dash is the velocity of the particle p according to O dash, and b is the velocity of the particle p according to O. Okay, so as we have derived r dash equals r minus bt, okay, so we can differentiate this equation in order to get the velocity of the particle, because these are the position vectors, and the first derivative of the position vector gives us the velocity. So let us differentiate this equation. This is dr dash over dt equal dr over dt, and this is, as v is constant because particle p is moving with the constant velocity v, so this can be taken out from the operator. This is dt over dt. Now also time was absolute, t equals to t dash, so dt will equals to dt dash. Okay, so I am taking it as dr dash over dt dash, because whatever the dt dash is, it is also equals to dt, and it is dr over dt, no change, and this is dv over dv, dt is cancelled by dt. This is simple v. Now this is the derivative of r dash with respect to t dash. Okay, so this gives me the velocity of the particle p, observed in the s dash kind of frame of reference. Let's say this is v dash. Okay, this is v dash. No, I am saying it as u dash. Okay, this is u dash, and this is the velocity of the particle p observed in this kind of frame of reference by this observer. Let's say this is u, and v is nothing but the velocity of the particle, actual velocity of the particle. Now this equation says that the velocity observed by an observer O dash, which is placing in frame of reference as dash, is v value negative from the actual value, from the velocity of the particle p observed by the O dash. It means that the velocity observed by the two kinds of observers in different kinds of frame of references are different. It means that there is no variation. There is a variation. There is a variation in the velocity. Okay, there is a variation in the velocity of the particles in two inertial frame of references. Okay, because the u dash is the velocity. Let me write it as velocity in s dash frame of reference, and u equals to velocity in s. What are different? Because u is u and u dash is u minus b. So there is invariance in the Galilean transformation of there is no invariance of the velocity of the particles which are observed in two kinds of systems. Okay, now if we are interested to find the acceleration invariance, then that will be, let us differentiate this equation one more time. That will give me du dash over dt, and it is equals to du over dt and minus dv over dt. Sorry, this will be 0 because v is constant velocity of the frame of the particle. The differentiation of a constant value is 0. Okay, now du dash over dt can be written as dt dash because dt equals to dt dash. Okay, so du dash over dt dash gives me the acceleration observed in the frame reference as dash, and this gives me the acceleration because this is the derivative of the velocity observed in the frame reference s. So this is the a dash equals to a. So there is a dash equals to a. So whatever the acceleration in frame of reference as dash is just the same in the acceleration in the frame of reference s. So Galilean transformation are invariant. We can say that Galilean transformations are invariant in the context of the acceleration, or acceleration is invariant in all kinds of inertial frame of references. So let me write here, velocity is not invariant in inertial frame of reference while acceleration is invariant. So you must remember these two things whenever you come across the invariance or invariant in the relativity. Then velocity is not invariant, but acceleration is invariance in two kinds of inertial frame of references. Okay, so I think this is enough about the basic concept of the general idea of relativity. If we add some more topic in this video, then that will be longer. So we will meet in the next video. Thanks for watching.